You know how you can watch your shadow shrink and grow all day and not really think about it? Well, what if I told you that simple observation is actually the first clue in an incredible cosmic detective story? Today, we're going to follow that clue from the ground right under our feet all the way out into the cosmos to understand Earth's amazing dance, its spin, its orbit, and the incredible shadows they create.
So, let's meet Rashmika. She's on her way to school, and she notices her shadow is super long in the morning, but by lunchtime, it's tiny. Her first thought is pretty logical. The sun must be moving. But then she thinks, wait a minute, I learned in school that the Earth is what's moving. So what's the real story here? That is a fantastic question, and the answer is way cooler than you might think.
All right, to solve Rashmika's puzzle, we have to start with the first piece, and it's a motion that's happening to every single one of us, right now, even though we can't feel it at all, our planet's daily spin.
It's kind of wild, right? Our senses are telling us we're perfectly still. But in reality, we are all passengers on this gigantic cosmic merry-go-round that is constantly, and I mean constantly, spinning.
Think about it like this. Picture yourself on an actual merry-go-round. As you spin one way, everything outside, the trees, the benches, your friends, it all looks like it's gliding past you in the opposite direction. It's just a trick of perception. Well, the Earth is our merry-go-round, and the sun, it's just like one of those stationary trees. It only appears to be moving across our sky.
So, this daily spin has an official name. It's called rotation. The Earth is spinning around this invisible line that goes right through its center, from the North Pole to the South Pole. And this whole turn, from west to east, takes about 24 hours to complete. This is the first major key to figuring out Rashmika's shadow puzzle.
And just think about what this one simple spin does for us. It creates the most basic rhythm of our entire lives, the cycle of day and night. And because our planet is spinning from west to east, it creates the illusion that everything up there, the sun, the moon, all the stars, rises in the east and sets in the west.
And you know what? This is not some new idea. Way back in the 5th century, the brilliant Indian astronomer and mathematician Aryabhata totally nailed it. He said it's just like being in a boat. As you move forward, all the stuff on the shore that's standing still looks like it's moving backward. It's the exact same idea, just on a planetary scale. But here's the part that just blows my mind. Back when most of the world was convinced the Earth was the center of everything, Aryabhata said, nope, it's spinning. And get this, without any modern technology, he calculated that a full rotation takes 23 hours, 56 minutes, and 4.1 seconds. I mean, that is ridiculously close to the number we use today. Just an absolutely incredible achievement.
Okay, so rotation explains why the sun seems to move across the sky each day. Puzzle solved, right? Well, not quite. That's only half the story. While our planet is doing its daily spin, it's also on a much, much longer journey through space.
This second big movement is called revolution. As the Earth is spinning like a top, it's also traveling along this huge path, its orbit, all the way around the sun. And this epic road trip is what we call a year. It takes about 365 days to make one full lap.
And this revolution is also why our view of the universe keeps changing. As the Earth moves around the sun, the patch of space we're looking out into at night changes. That's why we get to see awesome constellations like Orion in the winter, but they're gone from our night sky in the summer.
Now, revolution brings us to a huge question. Why do we have seasons? So many people think it's because Earth gets closer to the sun in the summer, but that's a myth. In fact, for those of us in the northern hemisphere, the Earth is actually closest to the sun in the middle of winter. The real reason is so much more interesting, and it's all because of a little lean.
You see, the Earth's axis isn't perfectly straight up and down. It's tilted. And that tilt changes everything. When it's June, the northern hemisphere is tilted towards the sun. This means the sunlight hits us more directly, it's more concentrated, and our days are longer. Hello, summer. Then, in December, we're tilted away from the sun. That same sunlight gets spread out over a bigger area, so it's weaker and the days are shorter. And that's winter.
So this tilted journey creates 4 key moments in our year. We've got the solstices, which are the extremes. The summer solstice, around June 21st, is the longest day of the year, and the winter solstice in December is the shortest. Then you have the equinoxes, in the spring and fall, which are these perfect balancing points where day and night are almost exactly the same length.
So we've got a planet that's spinning daily, orbiting yearly, and doing it all with a permanent tilt. But what happens on those super rare and spectacular moments when all these moving parts line up in a perfect cosmic straight line? Well, that's when we get the grand finale.
This leads to a fantastic question. I mean, the sun is gigantic. It is 400 times wider than our moon. So how in the world can our tiny little moon possibly block out that entire massive star during a total solar eclipse? It just seems like it shouldn't work.
The answer is this beautiful cosmic coincidence, and it all comes down to a concept called apparent size. See, how big something looks to you depends on two things: its actual size and how far away it is. You can try this right now. You can hold up your thumb and completely block out a friend's head if they're far enough away. Well, by an amazing stroke of luck, the sun is 400 times wider than the moon, but it's also about 400 times farther away. The result? From here on Earth, they look almost the exact same size in our sky.
So, a solar eclipse is all about perfect alignment. As the moon orbits us, it sometimes glides directly between the Earth and the sun. When that happens, it casts this long, cone-shaped shadow out into space. And if you happen to be standing in the very small spot where the tip of that shadow lands on Earth, you get to witness the incredible spectacle of the sun completely disappearing.
And that alignment is the key to telling eclipses apart. For a solar eclipse, it's sun, moon, Earth. But if the Earth gets in the middle, its shadow falls on the moon, giving us a lunar eclipse. And here's the most critical difference for all you skywatchers out there. A lunar eclipse is totally safe to look at, but you should never, ever look directly at a solar eclipse without special, certified eye protection. So when you put all these pieces together, the spin, the orbit, the shadows, you realize our planet isn't just a rock floating in space. It's like a tilted dancer, constantly twirling on its own axis while sweeping through this grand orbital ballroom. It's a precise choreography with the sun and the moon.
It really is this beautiful cosmic clockwork. The daily rotation is the steady tick-tock of our day and night. The yearly revolution is the calendar that gives us a new view of the stars. And that all-important tilt, well, that's the secret ingredient, the magic that paints our world with the different colors of the seasons.
So now you're in on the secrets of our planet's incredible dance. But this leaves us with one last, really fascinating thought to chew on. We've just seen how absolutely critical that tilt is for everything. So what if it wasn't there? What if the Earth spun perfectly straight up? What would life on a planet without any seasons even be like? Something to think about. Thanks for joining me.